Welcome back. We have now seen that the moment equation in 3D would be the position vector r cross the force vector F. So this is the position vector, this is the force vector. They both lied on this blue plane, and then this r cross F, it gave you a moment vector that was perpendicular to the blue plane. And according to the right-hand rule, that was its sense of rotation. However, in reality, we don't think about those random planes on which we have those r and f vectors. We usually work in the Cartesian coordinate frame. And so let's see how the cross product looks like in the Cartesian frame. When I write this formula, the moment about point O equals the position vector cross the force vector, then in the Cartesian coordinate frame, this would be the position vector with its I, j, and k components, cross, and this would be the force vector with its I, j, and k components. And now what I will do, I will rewrite this equation like this. The first three terms that I have here is due to the fact that I take this Rx and I multiply it by Fx, Fy, and Fz. And when it's Rx times Fx, then you see that you have here I cross I. Then Rx times Fy, then you can see that you have here I cross J, so it's right here. And finally, when I multiply Rx times Fz, then since you have this cross sign here, you have to have here I cross K. It's this one cross this one. Then the next three terms that I have here, I get them when I take this Ry and then I multiply it by Fx, Fy, and Fz. And according to the same logic, you have here j cross I, it's this one cross this one, j cross j, it's this one, and then j cross k, this one, and this one. And then finally, the final three terms, you get them when you take Rz and then you multiply it by Fx, Fy, and Fz. And then here you will have k cross I, k cross j, and k cross k. It's this one cross this one, then k cross this one, and then k cross k. And now, how to know what all these cross products between unit vectors are? It's actually very easy. The unit vectors I, j, and k are all 1 in the x, y, and z dimensions, respectively. First of all, when you have I cross I, j cross j, and k cross k, then here you're crossing the same vectors. Your I is parallel to your I, j is parallel to your j, and k is parallel to your k. They have no perpendicular components, so thetas between them are 0 radians. For example, when you have I cross I, then essentially you have 1 times 1, these are their magnitudes, times sine 0 degrees or 0 radians, it doesn't matter, times this unit vector sub c, and well, since sine 0 degrees equals 0, therefore the entire thing equals 0. And the same logic applies to j cross j and k cross k. They're all zeros because they're all parallel to each other, but when you have a cross product, you need to have some kind of perpendicular component from one vector relative to another vector. Here you have b perpendicular, which is perpendicular to vector A. But you don't have that in these three cases. And now, since I cross I equals 0, j cross j equals 0, and k cross k equals 0, that means that this entire term equals 0, then this entire term equals 0, and this entire term equals 0. And since they are zeros, we can simply eliminate them. And now, in order to find the other terms, you simply apply the right-hand rule, and you see where your right-hand thumb ends up. So for example, when you have I cross j, then you go from I to j like this, and your right-hand thumb will point in the k direction. So you will have 1 times 1 times sine 90 degrees, because remember, you have 90 degrees between I and j, and then this unit vector, which would be positive, will point in the positive z direction. So sine 90 degrees, that's 1, and so in the end you will simply end up with 1 times k, or simply k. Or for example, if you have j cross k, then you go from j till k, again you have 90 degrees here, and according to the right-hand rule, your right-hand thumb will point in the positive x direction. This would be your result. And so j cross k, it would be I. Or for example, if I have k cross I, you go from k till I, you have 90 degrees here, your right-hand thumb will point in the positive y direction. And just like in the previous cases, the magnitude of that cross product will be 1, so it will be 1 in the j direction, but j already is 1, so it's simply j. So this is I cross j, this is j cross k, and this is k cross I. And if you go in the other way, then you have the opposite directions. For example, if I have j cross I, then you go from here till here, and then according to the right-hand rule, this will be your result, which is minus k. So j cross I equals minus k. Then k cross j, you go from k till j. According to the right-hand rule, you will get minus I, so it's this one here. And finally, when you go from I till k, then you have I cross k, and according to the right-hand rule, you will have minus j, like this. So this is j cross I, k cross j, and I cross k. In all these cases, u sub c would be minus 1. And so now, you can simply say that I cross j here, that's simply k, then I cross k, that's minus j, j cross I, that's minus k, j cross k, that's I, k cross I, that's j, and k cross j, that's minus I. Once this is done, you can take this entire equation and you can rearrange this entire moment equation like this. I factor out my I, and then I have this one in the parentheses, so that's this term and this term. Then I write minus j, and then I will have all this in the parentheses, so that's this term and this term. And then I write plus k, and then I have all this in the parentheses. So that's this term and this term. Note that in the second term, I have minus j here. And then I have all this in the parentheses. I could have written it like this as well. Plus j, and then rz times fx, which is this term, minus rx times fz, which is this term here. So they would have been reversed. So this one here and this one here, they are equal to each other. But I purposefully chose to write it like this. That's because if I write it in this way, then it's essentially a standard calculation procedure for a 3x3 determinant. So I can write the moment vector, and remember the moment is also a vector, just like a force. That's why I put this arrow here. It's r cross f, and now in the determinant, I first put ij and k here, then rx, ry, and rz, and then fx, fy, and fz. In order to calculate that, I first choose my I unit vector, then I cross out the first column and the first row, and so I'm left with a 2x2 determinant here. So I write I, and then I multiply it by a 2x2 determinant. Then what I do, I take this j unit vector, I cross out the middle column and the first row, and then here I write minus j, and then I will have a 2x2 determinant here, and it will consist of these four remaining elements. So rx, rz, fx, and fz. And then finally, I take k, I cross out the third column and the first row, and then I have these four elements left, and I write plus k, rx, ry, fx, fy, and this would be my 2x2 determinant. Now, just to let you know that this is a standard way to calculate a 3x3 determinant from linear algebra. I'm simply following a standard linear algebra formula. And now, what I need to do, I need to compute this 2x2 determinant, where you first multiply this diagonal, and then you subtract this diagonal like this. So you will have I times ry times fz minus rz times fy. Then you write minus j, and then you calculate this 2x2 determinant, rx times fz minus rz times fx. And then finally you will have plus k, then you calculate this 2x2 determinant, you have rx times fy minus ry times fx like this. And as you can see, it's exactly the same like this one here. This term is the same like this term. This term is the same like this term, and then this term is the same like this term. And that's why I put here a minus sign when I rearranged these equations, so that I would get the exact same form that I would get if I were to calculate this moment using the 3x3 determinant formulation. And now, all this in the parentheses, since you have this I unit vector here, this will be the x component of your moment vector. Then since you have minus j here, this one here, it will be minus my. So it's the negative y component of this moment vector. And then all this in the parentheses, since you have your k unit vector here, you have mz here. So that's the z component of your moment vector. And so the reason why I put minus my here is because I have minus here, and so two minuses, they will give you a plus. And so in the end, you can write your moment vector about point O like this: mx times I, that's the first term, then plus minus my times minus j, and plus mz times k, or in other words, mx times I plus my times j plus mz times k. And there you go. That's how you get your moment vector in 3D Cartesian coordinates. Once you have your r vector and f vector in the I, j, and k form, you can get your moment vector in the I, j, and k form as well. And now you're equipped to solve this flag and post problem. What is the resultant moment vector about point O due to these two tension forces in the cables in the I, j, and k form? What is this moment? Before I let you do it by yourself, I want to give you a hint that might help you get the result faster. And the hint is this: there is a distributive law of addition with cross products. So if I write A cross, and then in the parentheses I have B plus D, and they are all vectors, then I can rewrite it like this: A cross B plus A cross D. So this law might help you in this exercise. Think about how you can apply it to the problem. And well, try solving it first by yourself, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this flag and post exercise here. First things first, I want to decompose these two forces into their I, j, and k components. For that, I obtain the displacement vectors from A to B and from A to C. So let this one be R, AB, and this one R, AC. From the previous sections, you already know how to obtain them. You simply walk from point A to point B and point C along the x, y, and z dimensions. So RAB, that's 0i plus 2.5j minus 6k, and then RC, that's 2i minus 3j minus 6k, and they're both in meters. Then the magnitude of RAB, that's 6.5 meters, and the magnitude of RAC, that's 7 meters. And so FAB, that's the magnitude of that vector times the displacement vector over its magnitude. So it will be all that, this is the magnitude, 780 newtons, times, and remember that this one here, that was your general unit vector from A till B. Its magnitude was 1, and it had the same direction like this force vector. That's your U sub AB. And so in the end, that will be your force vector in the I, j, and k components. You have expressed this one using the I, j, and k components. And then you do the similar thing with force AC. You have its magnitude, you create this ratio, 420 times, and then all this. This is your general unit vector from A till C, which is this one here. Its magnitude is also 1, and that's how you express your AC force vector in your ij and k components. And so you have two forces that create a moment about point O, and now since they both originate from point A, from here, for both forces, you will have the same position vector or the same moment arm that goes from point O till point A. So this vector here, that's your position vector OA that you also need for your moment calculation, because you want to calculate your moment about point O. The position vector OA, you can see that it's 0i plus 0j plus 6k. And now I could simply calculate this resultant moment about point O by first computing the moment due to this force FAB, and I would do it in this way: the position vector cross and then FAB, and then I would calculate another moment due to this force FAC, so I will have ROA cross FAC, and then I would simply add these two moments together. It would be a simple vector addition, this term plus this term. However, remember that hint that I gave you earlier: A cross B plus D equals A cross B plus A cross D. Since both moments have the same moment arm here and here, and subsequently here and here, we can use this property here to calculate this moment in an easier way. So MRO equals, that's the original form, but just like you were able to factor out this A vector here and write all this in a more compact form here, you can also factor out this position vector here, and you can simply rewrite it like this: ROA cross FAB plus FAC. But this one, that's simply the resultant vector of these two vectors. So this equation can be also written like this: the position vector cross and the resultant force vector. Essentially, you would calculate the resultant force first, and then you would use it in the moment calculation. So let's do exactly that. So FR equals FAB plus FAC. This is FAB, this is FAC, and this is the final result. And now the resultant moment would be the position vector cross FR. So this is the position vector cross, this is the resultant vector, this is the 3 by 3 determinant, this is the I component, then minus j times, and this is the 2 by 2 determinant for the j component, and then plus k, and that's the 2 by 2 determinant for the k component. And so if you write it all out, then this is how it looks like, and this will be your end result. Your resultant moment vector about point O in the I, j, and k components will be this one, in Newton meters. It makes sense because your forces were in newtons, and then your position vector was in meters. If you try to graph it, then you see that it has a negative x component, so somewhere here maybe, then a positive y component, which has the same magnitude, so maybe it's somewhere here, and then it has no z component. So in the end, your moment vector would be something like this. It would start from point O and it would reach this point. And so this one would be minus 720 Newton meters, this one here, and then this one would be 720 Newton meters, which is this one here. And again, there is no z component. And according to the right-hand rule, where your right-hand thumb needs to point in the direction of this arrow, when you curl your right-hand fingers around this arrow, from that right-hand rule, this would be its sense of rotation. And also it makes sense that your moment has no z component. This is your position vector, but it only has the z component. And so when you take your fr vector, which has all three components, however, when you cross them, then this cross product will only take the components of this fr vector that are perpendicular to the position vector. So you would have something like this. This is your position vector only in the z dimension, and then the cross product will decompose the fr vector in such a way that only fr perpendicular will be multiplied by the position vector. And again, remember, this is the z dimension, and so when that happens, then you will have a moment on the xy plane, but it cannot have a component in the z direction. Thank you very much.